here's kind of the meat of what a Metalog distribution is. You don't have to memorize any of the equations. They're all in my paper. They're already implemented in various software platforms, but it's important that you have at least a basic understanding of what's going on. Now, this equation here is one of the simplest equations of a probability distribution that I've ever seen, and I've always liked it ever since I saw it in graduate school. I thought, wow, is that incredibly simple. This is the equation of a logistic distribution. If you're not familiar with the logistic, it's very much like the normal distribution. It has infinite tails on both ends. It looks a lot like the normal distribution. It's symmetric. It's just a little bit skinnier, and its tails are a little bit fatter than that of the normal. The equation is so simple. If x is your variable of interest on the horizontal axis, that can be expressed as a mu, which is the mean of the distribution, plus an s, and s is, I think it's the standard deviation over 3. Anyway, think of it as proportion, or over the square root of 3. Anyway, think of this s as being controlling the width of the distribution, the standard deviation. And then this log of y over minus y says, depending on where you are on this y-axis, you have a large value for x or a small value for x, okay? So there's a distribution. It's a well-known distribution. I didn't invent this. It's been around for a long time. In fact, there's a 690-page book called the Handbook of the Logistic Distribution that was written by Professor Balakrishnan, who's one of the 3 authors of the continuous distributions book I showed. And so this distribution is very, very widely used in practice, in industry, for various things. This is called a quantile function. This is x as a function of y, and it's also a so-called F inverse. You've seen capital F to the -1 of y, where y is your cumulative probability. That's officially called a quantile function. That's the thing you like to use for simulation, and that's the thing that I wanted to use. I wanted to express the CDF as a quantile function, that is x as a function of y, primarily for ease of use in simulation, but it also has critical advantages for fitting data, as you will shortly see. Anyway, the Metalog, what is a Metalog? Metalog is short for metalogistic. It is a modification of the logistic distribution. Well, what modification is that? Well, I started off with a thought. The thought was, what if this standard deviation S, instead of being a constant, were to smoothly increase as you go from smoothly increase as you go from left to right on the density function. Standard deviation gets bigger and bigger and bigger as you go from there to there. Well, wouldn't you think that what that means is the standard deviation that controls the width of the distribution is smaller over here and it's bigger over here. So that presumably would lead you to a right skewed distribution if you made this modification to it. And in fact, that's precisely true. If you just if you made this standard deviation a linear function of your cumulative probability y, you get all these various shapes shown here, depending on what your settings of A3 is. What if you ask the same question about mu? What if the mean of the distribution were to smoothly increase as you go from left to right? Well, that would say that you're fuzzing up where the center of the distribution is. So if mu were to smoothly increase, at least intuitively, you might think you'd get a fatter distribution. Well, that actually turns out to be the case. With this simple linear modification, you get all these different shapes, everything from a uniform distribution exactly, all the way up through distributions that have very fat tails, like student t distributions of 2 or 3 or 4 degrees of freedom. Those were the original Metalogs. That's what we used for 2 or 3 or 4 years. Before we finally had an additional insight, which is, well, why stop there? Why not add additional terms in a power series to add further ability to describe the nuances of how the standard deviation changes with cumulative probability, how mu changes with continuous probability, and let's find a way, if we can, to specify those A coefficients using data. So that leads us, if you just make these substitutions, substitute this series in there for mu, substitute this series in there for S, the other way around. Substitute those 2 series in there, you end up with an equation. And this equation is the basic Metalog distribution. And this is x as a function of y, and it can have any number of terms. There's a two-term Metalog, which is the logistic distribution exactly. If you just use the first three terms of this series, it's a three-term, first four terms, five terms, and so forth. Okay, I've got it all the way up to 10 terms, but you can have any number of terms. In principle, you can have an infinite number of terms. It's just like a Taylor series in that sense. Each additional term defines a different probability distribution. That is, a three-term Metalog distribution and a four-term Metalog distribution are not the same unless this constant A4 happens to be 0. Okay. But each additional term adds shape flexibility. You can capture more and more shape flexibility of your data, as we will see. There are about 60 practical distributions in the Metalog family. That is, the practical numbers of terms when you program this up might range from 1 to, or maybe 2 to 16. That's 15 distributions. But we also have four choices of boundedness. We can have unbounded Metalogs, we can have semi-bounded, we can have bounded, and semi-bounded can be either way. So, and I'll show you how that works. But this is the basic Metalog equation. And one of the things I would note here is look how simple this equation is. You might say it's a complicated equation, but really it just consists of a polynomial, some of which terms are multiplied by this log of y over 1 minus y. This is a whole different thing than what you get with the Pearson distributions, where you've got gamma functions and beta functions and whatever it is, such and such functions of the third kind, you know, that they're complicated statistical functions that are hard to evaluate. This is a simple equation you can program on any platform, including in Excel, very, very easily.